Saxon Algebra 2, Lesson 25. Multiple topics today. The first one is, sounds so much worse than it actually is. It's called monomial factoring. But I would say it's called easy factoring. Here's what I want you to remember. You know how we learned how to distribute? And we learned that if you have something like this, you can multiply the a times the b and the a times the c, and what you'll end up with is ab plus ac, right? In fact, we'd multiply those two and then those two. That we call distributing. What if you have it in this form and you want to put it back into that form? You want to look at this and go, oh, look, there's an a in both of those. So I can pull that a out and have b plus c left. Going like this is called factoring. Okay? So factoring is simply undoing distribution. And distribution is a form of multiplying. And so factoring, I don't think of it as division, but I think of it as undoing multiplication. Okay, so if you can kind of keep this picture in your head, that will make this fall into place quite quickly. Let's look at an example. Factor is the instruction 4ax squared plus 4xy. Now, just to make this super duper easy, I'm going to take this squared and I'm going to say, let's just write it out, right? That 2 stands for x times itself 2 times. So I'm going to write it like this. We won't do this every time, but just to make it super clear what we're doing, all right? So this and this are the same thing. Now, what I'm looking for is, just like here, I'm looking for which pieces are the same in the two different terms. I can see that they both have a 4. This one has an a, this one doesn't. This one has 2 x's, this one only has 1, so they have 1 x in common. And this one has a y, but this one does not. So what I can pull out of these, and we call it the greatest common factor, equals 4x, right? That's what each pair has. The greatest common factor is what we call the a in this picture. So that goes on the outside, and then in the parentheses, I'm gonna write what's left behind. Just like here, when I pull the a out of both of them, I have a b left behind and a c left behind. What's left behind from this first term when I pull out the 4x? Well, there's an a and there's another x. This sign always stays the same. And when I pull this 4 and x out, as I did here, I get a y. So this is my final answer. You can always check the answer of your factoring by distributing. If I multiply this times this, I get 4ax squared, yes. And here I get 4xy, yes. So you can easily test and make sure you got it right. Oops, I turned 2 pages. So excited, I just started a new book, so I'm just trying to race through it. Example 25.2. There are a total of 3 examples in this section, and then we'll move on. 25.2. All right, this one's a little bit more involved. All right, I'm not going to take the time to write out the exponents like I did the first time where x squared, I wrote x times x. This time we'll just imagine it in our heads. And I'm just double checking to make sure I got this right. Okay, It helps me a lot if I put these in alphabetical order, but I didn't do that, so I'll show you another trick for keeping our head on straight. But first, we're gonna turn our attention to the number, 4 and 6. What's the most I can take out of those two numbers? 2. Okay, now I'm not in alphabetical order, but I'm just gonna go in the order of this term and compare it over here. Here I have an x squared, here I just have a plain x. We can take out the lower of the two values. So x. P squared, p to the fourth, we can take out the lower, so it's p squared. And k squared, we can take out the lower, so it's k. Make sense? Again, this we call the greatest common factor. Now we compare this to this and say, what do we have left behind? 2 to 4, let's see, there's another 2, another x. We took all the p's and we took all the k's. Okay, so that's the end of that. Minus sign stays the same. Now we compare to the 2 to the 6 and say, okay, we still have a 3. X to x, we took that. P squared to p to the fourth. So we still have 2 p's left over here. And then k to k squared, so there's a k. So our answer is 2. John says 2x p squared k. Okay, that's the same as us. Times the quantity 2x minus 3k p squared. So he has the same pieces, just in a slightly different order. Order doesn't matter when we're multiplying. So yay. Again, if we wanted to, we could check this by distributing it and making sure we get back to that. Okay, one more of these, and then we will shift topics a bit. Again, the instructions are to factor. It's pretty straightforward. Oh, this one is a 3-parter. Not necessarily harder, but we just have to compare 3 things instead of 2. All right, start with the number always. 4, 2, and 10. What can we pull? They're all even numbers, so we can take the 2, can't we? All right, and I'm just gonna look at the letters here. There's an x squared, an x, and an x. We take the lower, so that's a plain x. Y squared, we take the y. This is what we call our greatest common factor. That's what goes on the outside. Then we compare that back to each term to see what's left behind. Here, let's see, there's a 2 and there's an x, right? Because we took an x, but there's an x squared. We pulled the full y, so we're done with that. Now, here's a tricky one that a lot of students trip over the first time through. Look at our second term. There's a minus sign. We pulled the 2, we pulled the x, we pulled the y. There's nothing left. Some students think, well, we don't write anything down. No, we have to write a 0. And I'll prove that to you in just a minute, but let's just go on. Now I put this plus sign. 2 to 10, that says there's 5 left. We took all the x's, but there's still 1 y, right? Now, how do I know I did the right thing here? Because if we distribute, we need to be able to get this back. So here we'd multiply this by this. Yeah, we'd get that. 2xy times the 1 gives us that back. If we just skipped that and said it's 0, we don't even have to write anything, then we wouldn't get that middle term back and we'd know we had made a mistake. That's how we can be sure, because we have to be able to get that back. This is the right answer. Okay, so if your greatest common factor is equal to the full term, then you use a 1 as a placeholder. Okay, this topic is closely related to our next topic, which is cancellation. And this is one of those disappointing moments in math when you realize things aren't always as easy as it seems like they should be. Let's say that we have this problem, this expression floats up, and we want to cancel it. And we go, oh, look, we can cancel all these 4s. No, we cannot cancel here. There's no canceling allowed. Do you know why? I'll tell you. Because whenever we try to cancel the bottom four against one of these in the top, these are being added. This is why we're not allowed to, because we're adding, or if you're subtracting, it's the same problem. If there's an addition or subtraction sign up here that is directly involving the numbers you want to cancel, you're not allowed to do it. However, we can factor first, and that creates lovely options for us. So in this problem, what we would do is we would pull out the 4. We would look at this and go, oh, look, greatest common factor of 4. Pull it out. We get x. It takes the whole second term, so we have to use a 1 as a placeholder. Right? So we factor. Now we can cancel. And our answer is x plus 1. Isn't that cute? So if there's addition or subtraction, there's no automatic canceling allowed, but you can factor first, and then you may be able to cancel, like this one. Let's try, that wasn't an official example. I'm sorry. There's just one, 25.4, but John does the tricky A, B, there's just an A and a B. That's so sneaky when he does that, right? It's like, that's 2 problems, John. Don't pretend that it's not. Okay, we see X's all across the board. Our eyes light up. We want to start crossing things off, but we can't. That plus sign throws a giant monkey wrench into the process. So we have to factor first. So we'll pull out of, let's see, we only have to factor in the top, by the way. The bottom's just a single term, so it's the top. We can take an x squared out of both of them. So we'll take x squared, and then in the first one, we'll have 6x left. And we took the whole second term, so that's a placeholder, just a 1, over x squared. This cancels against this, and so our final answer is 6x plus 1. Okay, so we were able to happily cancel there. All right. The second one is the real heartbreaker. B. Don't you just want so badly to be able to cancel those 2x squareds? And we see this, and we go, no, we're not allowed to cancel. Shoot. Okay, well, let's factor. We'll be able to factor and get it out. And then we look at these two and go, they have nothing in common. They have nothing in common. They have no common factors whatsoever. So there's nothing we can do. And we just have to leave that. It's like when you're picking blackberries in the summer. This happens to me every year. And you see the biggest, juiciest clump of berries, and they're just out of reach. And you stretch, and you try to use a stick, and oh my gosh, you get the tallest person in your family over there, and no one can reach it. And you just have to leave those beautiful hanging blackberries, because there's no cancellation possible. Oh, so sad. Okay? There's nothing we can cancel because the 2 terms that are being added or subtracted have nothing in common. Okay? We can't factor anything out, and so we're just stuck. It's so sad. All right. The third topic is hardly even a topic. It's going into geometry. John just wants to make the point that parallel lines in triangles can be used as transversals. All right, I'm gonna do 2 of the homework problems for you so you can see how it works. Well, I'll start them for you. C, so this is homework problem 25C. Looks like this. Kind of, pretend it's perfect. It's a triangle with it's the color form triangle. 4, 3, 7, 5, X, Y. And it's got these lines on here, okay? Now, this indication tells you that these are parallel lines, okay? So whenever we see this notation, that means the lines are parallel. If those lines are parallel, then we can kind of imagine these as transversals, right? And this is the line cutting through. And you know how we have that larger, smaller pattern that always happens in transversals? Here, I'll just draw that separately. Larger, smaller, smaller, larger, right? Larger, smaller, smaller, larger. We can use that in a picture like this to go, okay, well, if these are parallel and this is a transversal cutting through, then this angle and this angle must be the same because they are both the smaller angles of these pairs, right? It would be, well, it's this one and this one match up, right? And in the same vein, I'm just going to switch this to purple so you can tell it's different. Pretend this is a transversal cutting through these same parallels, and we would have the same kind of pattern, right? This angle is going to be the same as this angle. It's going to be the smaller, right? And that would be the larger, smaller. So parallel lines can be used as transversals to identify matching angles. Okay? We just use these parallel lines to show that these angles are the same and these are the same. These are the purple angles, these are the red. All right, they don't match each other. They just match this way. Why is that important? Well, in this picture, we know that angle's separate, right? I've just proved angle, angle, angle. I've proved all 3 of these angles are the same. Because these lines are parallel, I know that these match and these match. And I also know that this is the same because it's a color form triangle, so that's the very same angle. So now I know I have angle, 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 and I can say that my triangles are similar, and therefore I can use proportions to solve. It doesn't work the numbers for me, but it tells me, okay, because you notice these are parallel lines, because you understand how transversals work, that means you know that these angles are the same, these angles are the same, that one's the same. You know that all 3 angles are the same. That means you have similar triangles. That means you can use proportions to solve. That's a lot of theory jammed between your ears right now. I don't know if you can possibly appreciate it, but I just want to show you how these parallel lines make it possible for you to use the proportions to solve, all right? And you know how to do that. Nothing's different about it. I just want to show you the other picture so you could go ahead and do that now. You already know how to do the calculations. We're just discussing theoretically why you're allowed to do that. I know, it's kind of a boring kind of problem. The D problem, homework 25, no, it's 26, no, it's 25. D looks like this. And the little parallel line markers are like this. Okay, well, it works the same way. We have to extend the parallel lines to help our brain see the transversal. And honestly, what helps me, I have to turn it because I'm used to my transversals. I'm used to the parallel lines running this way. Okay, so then this is one of the lines that chops it, a transversal. That means that the angles are going to be the same. That means that smaller, larger, larger, this is the smaller, and this is the smaller, right? Smaller, larger, larger, smaller. So that means these two are the same. And conversely, purple, if I consider this to be my other line that slices through those same two parallel lines, then I can say, okay, let's see, this is larger, smaller, this is the smaller on the purple line, and then down here, larger, smaller, this is the smaller on the purple line. That shows me that between these two triangles, I have two matching angles, plus I know that this one's gonna match, right? Because vertical angles are always the same. So that tells me I have angle, angle, angle. That tells me that my triangles are similar. And that tells me it's okay to use proportions to solve. Now, when I first started doing these problems, the point I missed is that if the triangles aren't similar, then you can't use proportions to solve. I never really appreciated that fine point. Okay, so yeah, you know how to use the proportions to solve, right? You find the anchor proportion and then you set up the ones one at a time for each of the letters that you want to try to solve for. We're only allowed to do that because we know that the triangles are similar. And we know that they're similar because of angle, angle, angle. And we know that the angles match because of the transversals. That's the point of this lovely lecture, all right? So the calculations that you're doing in C and D, these problems, the calculations you'll actually do are exactly the same. The only thing that's different is John and I are asking you to appreciate at a deeper level exactly what it is you need to know before you can use that proportion method to solve. Okay, I think I've prattled on quite long enough, don't you? That's 25. 26, we're gonna get back to business with some more factoring. And then we have some more triangle drama. So, you know, the pattern lives on. Algebra, geometry in each lesson. Okay, thank you. Goodbye.